Imagine looking at a picture of a dog. Instantly, your brain knows it's a dog. No effort needed. Now imagine I show you a cat and another dog. You immediately recognize that the cat has its own distinct idea and that the dogs represent the same concept, even though the values of each individual pixel in the two dog images are completely different. Your brain did this effortlessly. But here's the tricky part. If I asked you to explain exactly how you knew it was a cat, or to write step-by-step rules for a computer to do the same, the task becomes nearly impossible. That's where neural networks come in. In this video, we'll start from simple math and build up to a system that can recognize what digit a 28 by 28 image represents. In the following few videos, we will extrapolate this understanding to more complex LLMs like DeepSeek. First, I'll explain the theory and ideas behind our digit recognizer. Then I'll explain some of the math behind them. And then finally, we'll look at a fully complete digit recognizer in Python. Our digit recognizer is going to be a kind of neural network, which is a bunch of neurons interconnected into a network. We'll start off by looking at the structure of a neural network, then we'll explore the individual neurons these networks are composed of. Neural networks are built from neurons organized into layers, which pass information forward like a chain of decisions. Each neuron passes its processed information, in this case just a decimal number, to every neuron in the next layer unless it is an output neuron. The input layer represents the inputs we're asking the network to process. In our digit recognizer, each pixel has its own input neuron. Our digit recognizer is going to work on a 28 by 28 image, which turns out to be 784 neurons. Again, one for each pixel. The neurons in the hidden layer act like feature detectors. They transform messy pixel data into patterns that are easier for the network to reason with. Earlier hidden neurons might learn to detect simple shapes like short lines or curves. Deeper hidden neurons can then combine those into more complex patterns, like corners or loops. It's important to note that each neuron isn't necessarily looking for simple, recognizable shapes like loops or curves. That example is just to give you a general idea of what's happening under the hood. In reality, each neuron is detecting something much more abstract, patterns and features that the network itself only truly understands. We don't need to worry too much about that level of detail right now, so we can just move on. The key point is, we don't program these features by hand. The network discovers them automatically during training, adjusting its weights and biases until each layer extracts just the right information for the next one. That's why they're called hidden. We don't directly see what each neuron is looking for, but together they build up the knowledge needed to turn raw pixels into meaningful digits. Note that our task is relatively simple, so we can get away with only having one hidden layer, but the intuition still holds. The output layer has 10 neurons, one for each digit 0 through 9. The output neurons in our example will give a number 0 to 1, describing the probability of the image being that number. For example, when we give our network this image of a 3, it correctly outputs 0.8 or 3. This means the network is 80% sure that the image we gave it is a 3. A good analogy for the structure of our network is the following. The input layer is your raw ingredients, flour, eggs, sugar. Hidden layers are like the mixing, whisking, and baking that transforms the raw ingredients into something delicious. The output layer is the final cake. Now, the neurons themselves take in numbers, multiply them by weights, add a little extra called the bias, and then run the result through an activation function. The weights and bias are the network's parameters. Weights act a bit like volume knobs, turning inputs up or down. Biases shift the whole activation, letting the network learn patterns that don't neatly pass through 0. If we only had weights and biases, stacking layers would still just give us one giant straight line. That's not enough complexity to capture the messy curves of handwriting. Activation functions fix this by adding nonlinearity. They let the network bend and twist the input space instead of just stretching it. A common choice for the activation function is the sigmoid, which squashes values between 0 and 1. So the neuron takes data from each of the different neurons it is connected to, multiplies each input with its own special weight, adds a bias to the entire sum of all input neurons, pumps it through an activation function, and then finally sends the data to each output neuron it is connected to. One thing to note is that weights and biases are initially set to be random. The neural network has to learn the correct weights and biases that give the highest accuracy. You can teach the correct weights and biases to the network by first telling the network to predict a training sample. This is called a feed-forward. We use a cost function to then determine how wrong the network is, and gradient descent, which tells us how to improve. The process of learning these weights and biases is called deep learning. Neurons can thus be thought of as tiny little decision makers. They take in some input and, using their weights, biases, and activation function, decide their own output. The idea behind all of this is that when we set up the network with neurons, which are tiny decision makers that can learn, and organize them into layers, we will have created a system that is capable of learning to make complex decisions. Useful, it just has to learn by figuring out where it made mistakes and then adjusting its parameters accordingly. In order to teach the network the correct weights and biases, we must first figure out how poorly the network is performing. That's the job of the cost function. The process of computing the cost function is fairly simple. For us, it is simply the square difference between the correct answer and our network's answer, which is the output layer. The bigger the difference, the higher the cost, and the worse our network is doing. The lower the difference, the lower our cost, the better our network is doing. To summarize, the cost function takes in the network's answer, which is determined by all the weights and biases of the network, and spits out how bad the network is doing on a training sample. Now we need to make that cost as small as possible. This is where gradient descent comes in. Because the cost function depends on the output of the network, which in turn is determined by the network's weights and biases, we can express the cost function as a function of those weights and biases. This allows us to visualize the cost function as a surface, or a graph. Each combination of weight and bias values corresponds to a specific point on this surface, the xy position. And the height at that point represents how well or poorly the network does for that particular combination. In practice, however, neural networks have many weights and biases, so the cost surface actually exists in a very high dimensional space. This is nevertheless an accurate simplification. Our goal is to find the lowest value, the spot where the network makes the fewest mistakes. The gradient tells us which direction is uphill. To minimize cost and thus improve our network, we step in the opposite direction, downhill, little by little. Doing this on the entire dataset at once would be too slow, so instead we use stochastic gradient descent. It works on small batches of random data, say 100 images, figuring out the correct adjustments to each of the weights for each image, summing them and then applying them to the network. It's noisy but surprisingly effective. But here's the real trick. How do we know which direction to nudge each individual weight? Or mathematically phrased, how do we compute the gradient? That's where backpropagation comes in. Backpropagation is like the chain rule. It starts at the output layer, measures the error, and works backwards through the network. At each step, it figures out how much each weight and bias contributed to the mistake and thus needs to be adjusted. Then, the gradient of descent updates the weights accordingly. Let's look at some of the math behind how a neural network actually learns. A lot of this will make more sense once we dive into the code, so for now, we'll just focus on the most important part, backpropagation. To keep things simple, imagine a neural network with just one input neuron and one output neuron. Even though it only has two neurons, this network still has only one weight and one bias, since input layers themselves don't have weights or biases. Because this network hasn't been trained yet, its cost, which again is just a measure of how bad the network's predictions are, is high. Now, the cost depends on the network's output, and the output depends on all the weights and biases in the network. That means we can think of the cost as a function of all the weights and biases of our network. The goal of backpropagation then is to figure out how each weight and bias affects cost, so we can adjust them in the direction that makes the cost as small as possible. Or, mathematically, we want to minimize the cost function by using the partial derivatives of each weight and bias with respect to the cost. As a refresher, the partial derivative of a weight, W, with respect to the cost measures how much influence that weight has over the cost. In other words, how much nudging the weight nudges the cost. Before we get into the derivation, let's recall how a network's activation is computed. Each neuron takes a previous activation, multiplies it by its weight, adds its bias, and then passes that sum through the activation function. It's often helpful to label the value inside the activation function as its own variable. We'll call that value z. Now, let's draw a diagram detailing how numbers flow through our network. Notice how the weight and the cost function are pretty far apart. So instead of trying to measure the weight's direct influence on the cost, it's easier to break that influence down step by step, by how much the weight affects z, how much z affects the activation, and then finally how much that activation affects the cost. When you multiply all those together, a nice thing happens. A lot of the denominators cancel out and we're left with our original partial derivative. In calculus, this is called the chain rule. By the way, the variable y simply represents the correct answer we're trying to predict. And that's really the core idea of backpropagation. Same idea applies to biases, and even when we add more layers or neurons, the underlying math doesn't really change. If this still feels shaky to you, don't worry. Once we look at the code, a lot of this will be cleared up. First, we have the initialization method. Sizes is an array of numbers that tells us how many neurons are in a given layer. Here, we directly create the weights and biases for the entire network instead of creating individual neurons and assigning them weights and biases. Because if you set up the network like this, then you can take advantage of matrix multiplications, which end up being a really big optimization. Neurons will nevertheless be a helpful visualization. So, each neuron only gets one bias except the input layer. The weights are initialized a bit differently because each neuron except those in the input layer have weights for the layer before it. For example, the first entry in the stored network's weights has 3 arrays of size 2. The 3 arrays correspond to the 3 elements in the hidden layer, and the size 2 corresponds to the number of neurons in the layer before. The same logic extends to other layers. Feed forward is fairly simple. We just go layer by layer and apply weights, biases, and the sigmoid function accordingly. Now, the heart of our network is the backprop method. X represents the input to the network, in this case just the image of a digit. Y represents the actual numerical digit. Nabla B and Nabla W represent the changes we wish to make to every weight and bias of the network. The first thing we do is run a feed forward and store all the Z's and activations of the network. Then we compute the necessary changes to the very last biases and weights, which I just showed the math for. Then we work backwards and compute the necessary changes at previous layers in a similar way we computed the initial biases and weights. Once we are done running this function, we will have acquired all the changes we wish to make to the weights and biases of our network for a single image. SGD stands for stochastic gradient descent. Here, epochs represent how many times the neural network goes through the entire training dataset. It's similar to how repeatedly studying the same material helps us remember it better. Then we shuffle the training data and split it up into different batches, and we just train the network based on that mini batch. Now our update mini batch function, we take in a parameter eta, which just controls how fast the network learns in a way, which we'll see in a second. Nabla W and Nabla B represent the changes we want to make to the network's weights and biases respectively. And then for every image and the corresponding digit that image is meant to represent, which is the XY pair, we first run backpropagation to determine how much we want to change the weights and biases by. Then, after all the changes are collected, we update the network, scaling the changes based on eta. Note that making the eta too high will not make the network learn faster because the network just overshoots. For complete this, here are a couple of other helper functions. Evaluate takes in a bunch of images and the corresponding answers and spits out the answer of our network for each image. Note that because the network spits a probability distribution, we fetch the answer by taking the digit the network is most certain of. Here's the cost derivative, a reminder that output activations is our network's answer, again in the form of a probability distribution, and y is the actual answer. And here is sigmoid and sigmoid prime. Now, we can finally train our network. Here, we train the network with 5 epochs, meaning it goes over the entire MNIST training dataset, which is 50,000 images, 5 times. As we can see, the network improves with each epoch. Note that the accuracy drops a bit between epochs 2 and 3. This happens because we use optimization methods, such as stochastic gradient descent and a high-ish learning rate, that help the network learn faster but can introduce small fluctuations in accuracy and stability. And that's everything you need to know about neural networks. Because the video is short, some details were quickly glossed over and would have likely benefited from a more thorough explanation, but I think this video is more than sufficient as an intro to machine learning. Thanks for watching.